I'll introduce our invited speaker. So Dr. Brian Bockelman is an investigator at Morgridge Institute for Research, focusing on enabling research computing at the Institute on the University of Wisconsin-Madison campus and beyond. He joined the Institute in 2019, but has been working with the OSG consortium since 2008, providing the nation's flagship services for distributed high-throughput computing. In the past decade, Bockelman has been working on challenges of effectively delivering data to compute capacity, especially to the particle physics and astrophysics community. This work has evolved into the Pelican project, which is a $7 million investment by the National Science Foundation, led by Bockelman to expand and improve the Open Science Data Federation, which aims to connect data sets across all of open science. So if we can give a warm welcome to Dr. Brian Bockelman.
So ending the first little bit early is dangerous, because otherwise I get to talk longer about what I like. So I'm Brian from the Morgridge Institute for Research. It's a research institute right out on the UW-Madison campus. So if all else fails, you can say I'm from University of Wisconsin-Madison. But before I go into what our project's about, I want to talk a little bit how I got here. So nobody, I swear, ever starts a new project. You just take the crushed gravel foundations of all your old projects and build on top of that. So I have been working on this distributed high throughput computing approach since 2008, and I'm also a big proponent of what I like to call translational computer science. So first, high throughput computing. So this is all about taking a compute resource and maximizing the amount of science you can do that over long periods of time. So we're tend to kind of maybe differentiate it from what you might think of high performance computing. I'm a big fan of car analogies. So I like to say we don't want to build a Ferrari, the thing that can go as fast as it can in 1 second. I am building dump trucks, right? So I am interested not in how fast can you make your calculation go, but rather can you do 1 million of them? Can you, and especially since I'm focusing mostly on the distributed motion, not only can you do 1 million of your runs or your ensembles, but can you do them across the nation? So just limiting yourself to one resource. So all of that work involves a national infrastructure called the OSG, the fun little logo there. And then the other thing that's really important to me is the translational part of computer science. So translational medicine is a well-established field of medicine that helps take research discoveries way out at the fundamental labs and try to get them out to patients. And how do you actually make that connection? And computer science is really bad at that. Computer scientists love nothing more than coming up with a great idea, writing a paper on it, and then throwing it all away and waiting for the next great idea to come by. So we're really interested in production infrastructures, and we're interested in advances and approaches that can be valuable to scientists. And that means some things like we can't throw away an abandoned community as soon as we build it because we thought of something better. And for us, it also means that core to the research is the feedback. So I like to say none of our ideas ever move forward if we can't build a community and build users. That's actually part of why I'm here, is part of community building. So kind of an example, spacing messed up, but part of this one NSF project called PATH. We helped build and develop the HD Condor software suite. So that's actually been a project continuously funded or continuously developed since 1985 by Merle living at the University of Wisconsin. And for that translational piece, to gain insight of how it's actually used, the project runs what you think of as a virtual cluster called the OS pool. So about 60 different institutions all around the US all contribute resources, overlay maybe on their own batch systems, maybe through Kubernetes, maybe through their cloud instances. contribute capacity to this one centralized pool that covers the entire nation. And from that, scientists, about 60 institutions any given day have different individuals working on the OS pool. Science benefits, they get to use it, they get to advance their science, and we get that essential feedback of how our great ideas are wonderful or how our great ideas are horrible. And again, on the high throughput side, again, we really focus on doing many things, larger ensembles. So we complete about a dozen jobs a second, sustained throughout the year, 60 files a second, movement these streams. So just to give a visual map of the different institutions contributing to the OS pool, here we go. And I've noticed since we are in Colorado, I think that's Boulder and Fort Collins. So that's how I got here and what gets me motivated, what makes me tick. Why did I come here? One of the through lines of what I've been doing in the last dozen years or so is not just running the jobs, but jobs are sort of useless without data, right? You can maybe run simulations that you start with a random number, but other than that, data delivery is really essential for computing infrastructure. So we've developed this over the last 10 years, this infrastructure we call the Open Science Data Federation. And mostly it's been to connect people's data sources to the OS pool and do kind of support this distributed high throughput computing. And last year we launched and got funding from NSF to take that core idea of enable data delivery for this particular way of computing and start to broaden it and expand it. So one of the things I'm here for is to listen and learn how you guys use data, how you guys might fuse data sets together, what you might benefit from being able to bring the data to your compute, and listen, learn to the community, and hopefully you guys are going to teach me more than I tell you in this presentation. All right, so first let's get some of our definitions down. Pelican and the OSDF. Before I even get into what the Open Science Data Federation is, I like to say that my mantra is that the data sets are the lifeblood of science. We all can sit around, come up with clever algorithms, but for the wide majority of science, if you don't have the input data into those algorithms, you're not going to make the discovery, you're not going to make the advancements, you're not going to get where you want. And that said, with how important and central they are, the data engineering part of this is still really hard, right? If you look at, especially talks with people doing machine learning or AI, they talk about what percentage of their time is just the data engineering, the cleaning, getting it in the right place, getting the data sets together. It's always amazing to me how some of that nuts and bolts that people have to do take up so much of our effort before we get to that computation. So some of that engineering, some of the complications are on the software and infrastructure scale, as you get up into terabytes and petabytes. And then the reason a lot of I get into this is it's, I think, an inherently distributed problem. Maybe at NCAR we're a little bit lucky in that the archive and the computing are somewhat near to each other, at least physically. But that's not true in a lot of places. That a lot of times there is a mismatch between where our repositories are and where the available computing resources are for us. And trying to align those two can be a huge problem. So the Open Science Data Federation is the service that tries to take all these disparate data set repositories and make it easily available to whatever computing resources you have. So if I try to summarize into a sentence, I'm obviously not good at sales pitches, but the best one I come up with is it's a federated platform for delivering data sets from repositories to compute in an effective, scalable manner. So the way I think about this is somewhat, this is what it's like in my head, that we have all sorts of data set repositories laying around the planet. Some of them are huge. AWS, definitely has a budget of a couple billion more dollars than any of us do. We have various multiple sciences that all have their own repositories. We have maybe multiple repositories for single science. One of the ones that we've been working with really closely over the last couple of years is LIGO Laboratory, which has all the LIGO open and proprietary data. And we want on the bottom side to mesh those data set repositories with the different compute resources. So again, our background and where we grew out of is this virtual cluster called the OS pool, but we also want to deliver data to Jupyter notebooks and increasingly different presences and the different big NSF investments. So I guess the award that's spending the most money on machine learning and GPUs right now is this new one called Delta AI. So part of the project is we're working to grow from just where you see these existing stars to add more clients, so more things on the bottom, more integrated resources around the NSF community, and repositories and environments. So this is all the different parts of the OSDF. I'll explain a little bit what the different letters mean. You'll notice a couple things. One, this map's a lot more sparse than you saw for the OS pool. So we have about a dozen or so different repositories integrated as sources into the Federation. And then to actually distribute the data out, we use different caches located throughout the US. So when you pull down data from a very large compute resource, you're really apt to overwhelm the archive. Typically, archives repositories aren't set up for the wide scale resource or to deliver at wide scale. So we've been working with other projects to put physical hardware at different locations throughout the US. So our goal has been, I think we have it more or less, is to have a hardware within 500 miles from any site within the US. From here, the closest cache we have located is in Denver. And we're working with the team here to make sure that I guess I should put the arrow at Cheyenne instead of Boulder, but coming soon, some physical presence at NCAR. So the idea is when you want to request the data and you want to pull the data down, it gets pulled through these different caches. So you're not, or so you have fast, rapid reuse, and you have the nice locality of the data. So this is a difficult problem, and it's a problem that gets shared amongst a variety of different science communities. There's a lot of commonality. People have maybe a broad set of clients, but Python tends to be Python no matter what science you're doing. And it requires the scalable infrastructure that all those caches at different locations, NSF maybe has the resources to put hardware to blanket the nation, but not one for every single science domain that the agency or foundation supports. So the OSDF is kind of an approach to try to solve this once and maybe have some specializations for the community, but to have a shared core across all the different open sciences. And to give a view for just kind of what it is doing now, again, this is building, even though our project is 6 months old, it's building up on 10 years of work. There's about 15 different science collaborations that utilize the Federation within single PI teams on the OS pool. Outside of any collaborations, there's 120 different groups. We move about 60 files a second, which I immensely enjoy because it's about the same hertz as a light bulb. And over the last year, we moved to 64 petabytes. So it's on it may not be Google scale or Amazon scale, but as far as domain science, it's not trivial. And just to acknowledge the different set of folks that contribute. My project, Pelican, provides the software for the service. This other project operates the services. Path and the National Research Platform operates most of the hardware. So this is kind of one of those where we have quite a lot of effort, a lot of work to do, and we split and work together collaboratively projects. And hopefully we'll start filling out more spaces. All right, so that's the mantra and the vision. That's the boring part. How do the bytes actually flow to your notebook? So whether you're a batch worker node running the OS pool, or you're a Jupyter notebook sitting on a laptop or sitting elsewhere, the first step you have to do is know what objects you want to get. Notably, I like to think of myself as a plumber. I don't want to become a librarian or archivist or curator. I don't decide how the metadata works or how the data sets are organized, but once you know the czar data set you want to pull in, once you've found the data you're interested in, you can feed it to the client, and I'm trying to make it accessible. So the Jupyter notebook within this fires up a client for Pelican. And the first thing it does is with that object name goes to a manager process. Ours happens to be located in Wisconsin, and says, I'm a client, I want to download this particular object. And the manager, first decision it has to make is what's the closest cache that's going to serve that particular client. So again, if I fired it up here today on my laptop, the closest cache is going to be in Denver. So the client gets told, hey, it's great that you want that object. Here's a service in Denver. Please go ask for it from there. So if the data that I'm looking for is already in Denver, it gets served up immediately. As you imagine, a bunch of computer scientists go long ways about how we do it effectively and quickly, and how we have all sorts of wonderful fast hardware. But the goal is it does this at a pretty high data rate. But otherwise, if there's a cache miss, that cache is going to go back to wherever the data might live. We call the service the origin, the thing that connects whatever your object store or file system, where the data repository is, into the OSDF. So it pulls data from the origin, which reads from whatever the repository is. So even though it's a work in progress, the hardware is powered and getting configured. The little in-car letters here are a little aspirational. That's something that we hope to finish by the end of the month. And then, again, that was the cache miss case. Our goal is, if you're repeatedly pulling this data over and over, that you hit the cache and hit the local cache and the local copy, whether it's embedded in the network or at your university, as opposed to reading over and over, putting load on the in-car repository. Even though a lot of what I've talked about is open data and making data sets accessible, part of the really hard thing we do is authentication or authorization. So over half the use these days is for proprietary data sets or things that haven't been published yet. So making sure people maintain control and only get to read their own data is important to us. And of course, it's essential when you want to do writing back. So in the open data application of OSDF, there's not a lot of writes back. That's typically curated by archivists separately, but a lot of the active support in the OS pool, clients can write back directly to the origin. Again, the different parts, we have the object store, wherever that original data set repository is. We have a cache service that serves up and feeds data to the client and keeps a copy locally if it can. We have the origin service that connects the repository into the system, and the manager that kind of orchestrates the entire ecosystem. But the goal is for maybe folks in this room, all you see is the client, and even though I say we're computer scientists bearing gifts, the goal here is to kind of have it be like magic. You type in the name or anything you want, and it comes to your Jupyter notebook and it comes in. And we see ourselves as, I like to think myself as a transport bus or an adapter plug. I always like the crazy little plugs that you buy when you're traveling that can go in 15 different countries. And that's what we want to do. We want to not just work with the climate community, but the physicists and the biologists and the NIH-funded people and all those strangers like that, be able to plug them into this common data federation. And again, we're aiming to be able to connect to all of open science. And for us, that means we have to have a network of interesting data sets connected, and we have to make sure that we have all sorts of the clients to meet the scientists where they are. Even though we're working on the in-car integration now, and I'll talk a little bit about what we're working on this month in terms of Python integration. If this sounds interesting, or even if the OS pool sounds interesting, you can actually go take this for a run today and actually download the software, or just get an account of the OS pool and do file uploads and downloads and run your jobs there. So as I was thinking about this talk and trying to, not just give the high-level sales pitch of how this might benefit ESDS, this is a couple of things that we've been working on. So what we do is all distributed. What we do internally is all over HTTP. And if you add those things together and throw in buzzwords, that tends to be in that our infrastructure works well with anything that calls itself cloud optimized. So of course, if you're a stranger like me to this community and want to go start somewhere, you go to Project Pythia, and we've been looking at the different examples of reading ZAR formatted data, because that's kind of the closest to what we do. We pull in lots of data remotely and allow direct data reads over HTTP. So what we've been working on is taking this screenshot on the left, which is Xarray, AWS, and ZAR, and working towards the screenshot on the right, and doing Xarray, Pelican, and ZAR. So trying to say, can we take just those couple of little pieces that are S3 specific and replace them with a Pelican library? So might this be interesting? AWS is wonderful. I've had plenty of salespeople try to take me out to fancy lunches, but the compute you have may not be an AWS, despite what their salespeople want. So you might have that mismatch where the data sits in one place and the compute you have access to sits in another. AWS particularly can be cost prohibitive if you ever try to get a GPU out of AWS. They love you because they're making lots and lots of money off it. I think this might be interesting because maybe the data set you're interested in isn't actually in S3, and you can't use all the S3FS and ZAR integration, but in another repository that isn't quite currently accessible from the outside. So maybe your data set's not in S3, it's stored in NCAR or another data set repository. Or maybe you want to upload outputs later to your favorite object store. So if you kind of go through the diagram, this is what we've been set up and working on in our prototypes. The data that we're using is the same data sets from the Project Pythia inputs. We put a origin service up in Wisconsin that sits and connects S3 to the wider infrastructure. We have that same national network of caches. Perhaps if I ran it on my laptop, we pull it in through the cache and internet to in Denver and go through the Jupyter notebook. And what we want to do is kind of give this experience. And Even though S3 on my diagram was way up at the top and my laptop's way at the bottom, I want to give that experience of maybe AWS is right next to me and living as close as I can. And this tries to give that feel of things staged locally, minimize the data transfer on and off campus if you've ever hit a bottleneck of actually trying to pull down your favorite data sets. And then, of course, leveraging the fact that ESDS and others within the earth sciences community have been really pushing towards Python, and all the wonderful things that we've done there can immediately benefit Pelican as well. So I know a lot of this group are users, but if you've ever tried to provide services, you might say, well, why not just set up a big file system over here and run it like that? And the answer is data management. And again, going back to this idea, data engineering is hard. It's expensive. Somebody has to care for the hardware. Somebody has to run it, select the software, move the data set, set quotas. When somebody fills up the file system, go around and say, oh, can you delete this big data set because we ran out? Actually, all this stuff is really hard. And our goal is to try to take this out by using this cache-based. So if you're command line junkie, we have a command line client that works a little bit like SCP, except instead, particularly when you're uploading data, instead of your SSH password, it integrates with single sign-on. If you like to get under the hood in things, I point out that in the end, our command line client is just an HTTP client with a few other dressings on top. So anything, any other command line client, my favorite one is curl, can talk to the data infrastructure. So even though we have our preferred clients, anybody who can talk HTTP can use the infrastructure. And what we have in progress is a FS spec plugin. So FS spec is the abstraction layer that something like X-Ray might use to access data. So you can have the different inputs for X-Ray. So if you look at the Project Pythia notebook, you'll see this little bit of code to produce some S3 URLs. And then through a couple different lines of Python, it creates these objects that then can be fed to X-Ray. So we create the URLs, and it's that familiar S3:// blah, 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 blah. You feed those into something from the S3FS module and create these different S3 mapped objects, and then feed them to X-Ray. So our goal is to take that and working to provide the same set of objects, except instead of S3 and pointing directly at Amazon, it goes through our infrastructure. So if you have an existing notebook, what you would do is that URL you already know how to construct against S3, change a couple components of it to point it at the Open Science Data Federation, change the libraries that you use to create the objects, and then at the end, feed it into X-Ray, and then the rest of that is just simply doing your science. And again, what we want to do is not just have something specifically set up for Amazon, but collect as many different data set repositories as well. So hopefully in the near future, we'll say, well, if this particular data set sat at NCAR instead of S3, you would make sure that you put in the NCAR prefix, but otherwise be able to pull it data. All right, a little bit on the project itself. Again, it's a recently funded NSF project that'll be going for 4 years. I like to think of us having 3 goals, which is to expand and advance and integrate as much as we can into this data federation, expand the different types of computing. Again, we came from this corner of computing where we're all about doing lots and lots of automating tasks and workflows and scaling that way. And we want to grow more into interactive machine learning, notebooks, these sorts of things. And then finally impact the science user communities, which is this one. So just to pull things out from the next kind of quarter, next couple of things that are coming up. We are continuously working to improve our integration with S3 and object stores. historically, a lot of the integrations we've done have been with file systems, and of course, S3, like endpoints are the next most popular things. The Python FSPec API is the top client activity we're doing right now. So we're hoping to get a preview. I was hoping to have something up in PyPy by this presentation, but it's looking a little more by end of January, first release at the end of February. And this is the one where I think it'll really allow us to work with this community as it enables integration with Xarray and ZAR, and if you're just doing Pandas directly or PyTorch, all the favorite Python data science applications. And then finally, in terms of science user communities, we're working to integrate new hardware at NCAR. That's actually not our project, but a project run by Dr. Schuster here. And we're just trying to help and enable that. And I'm hoping, just based on the fact that things are plugged in, that some of the NCAR-based data sets are going to be available maybe about first half of February. And then I do want to acknowledge we're not just a single standalone project, but this is part of a broader effort by the NSF that is called the National Discovery Cloud for Climate. This is a pilot run by OAC, which is kind of the advanced computing arm from NSF, as opposed to be in GEO, where I think NCAR is located. And this NDCC activity aims to federate all sorts of different computing investments, from hardware awardees to large computing centers, from cyber infrastructure, low-level services like us, to people doing actual domain science, and try to have some through lines where we can impact all the way on somebody's climate science, all the way down to new hardware. I like this little excerpt that I thought explains well what the NSF is trying to do here, that develop this National Discovery Cloud for Climate, which will federate advanced compute, data, software, and networking resources. So there's about 30 projects under this umbrella, and hopefully we can start helping make impact on the climate community in the next couple of years. So, before I let you guys pelt me with questions, I'll pelt with you guys with some. What are the data sets and repositories that are locked away that we should target? I've already mentioned AWS, Open Data, NCAR. Where else should we start knocking doors with this community? Could we host a copy of a specific data set, or if you're deriving or making a, say, ZAR formatted data version of the existing data set, is that something that we can host for you? Beyond Python or even within FSPec, what's particular functionality that's going to make a difference in your workflow? And then finally, since I can't help to lead a pitch for path, if you ever find yourself saying, geez, I want to run a couple million ensembles, is that something that we can help run on those? So we're about 6 months into the project, out 4 years. It's still great early time to provide feedback and give us directions. And I'm looking forward to chatting with you now, or at lunch, or when you throw tomatoes in. So thanks a lot. Any questions?